Okay, sweet, cool. So yeah, the first few talks this morning were looking at melt inclusions and fluid inclusions and the kind of volatile content of them and how we can calculate the pressures that they're entrapped. And then I'm going to give a bit of a kind of primer on volcanic gases. So I guess this is ultimately where all those volatiles that are trapped, well, they're in the magma, come out at the surface. And this is a picture of Volcanic White Island in Aotearoa New Zealand. And you can see lots of examples of volcanic gas emissions in this picture. So just as, I guess, a reminder, or for those of you who don't normally think about volcanoes, essentially volatiles are kind of elements and species that prefer to be in the magma or in the melt at depth. And then as the magma rises to the surface, these species want to go into the bubbles. So you'll get nucleation of bubbles, and then these bubbles will grow. And the volatiles, which are things like water, CO2, sulfur, chlorine, etc., will go into these bubbles. These bubbles reduce the density of the magma and mean the magma is more buoyant, and so help it rise to the surface and ultimately erupt. And it's the expansion of these gases that causes like fragmentation and things. The interesting thing about the composition, the chemical composition of the bubbles, is that it changes as the magma pressure decreases. So when magmas are deep, the composition of the bubbles tends to be CO2 rich. So we have more CO2 present than water. And that's because CO2, as a volatile, prefers to be in the vapor, basically. It's quite insoluble relatively. And so it tries to go into these bubbles early. We continue to rise, and basically the bubbles become more water rich. And this is as water starts to exsolve from the melt into the vapor. And then we also get other species starting to go into the bubbles. And typically the pressure that this occurs is variable, but then sulfur starts to go into the bubbles more towards the surface. Now, actually, the volcanic gas is the only part of the magma that can reach the surface prior to eruption. So this is our best bet at having sort of actual material that's from the magma. And this means that we can measure the gas composition and try and infer something about the magma below. And it turns out that we can measure its composition. And because each of those volatiles has its own kind of solubility law and is really pressure dependent, we can start to maybe calculate magma depth based on the vapor composition. And we'll be like showing some of those calculations in exercise too. And so this kind of idea that you can calculate magma depth from vapor composition has been used at a variety of volcanoes. So this is a study from 2007 on Etna by IOPA, where you can see they've measured the CO2 to SO2 ratio in the gas coming out of Etna. And then they've converted it using one of these degassing tools that we talked about in exercise 1 and we'll show more of in exercise 2. And they've calculated a pressure. And you can see that just before the eruption, we have this high CO2 to SO2 ratio. This was also shown in Eko's talk for Turrialba, suggesting a deep injection of magma. And I have actually the same example, but basically same volcano, but different figure, showing that we see these high, oh, there's lots of data here. These high carbon to sulfur ratios, indicative of deep magma being injected into the system. So we can get volcanic gases released during eruption, but also we can just get volcanic gases released quiescently in between eruptions. And that's because in some cases, the gas can decouple from the magma and rise to the surface. And I just put some pretty pictures up basically of what these kind of emissions look like. So you can get bubbles coming up through like lakes and little lakelets here. A really common emission is fumaroles. So this is where you've got kind of a crack in the ground and you've got high temperature gas coming out, anything from maybe hundreds degrees all the way up to kind of nearly 1,000 degrees in some cases. But also, and this is the final photo, which is Nautahoe, sometimes the gas emissions are invisible. So this might be that it's just diffusively coming out through the ground, so diffuse soil degassing, or it could be that there is a plume coming out of Nautahoe, but we can't see it, and that's like an invisible gas plume. So a really wide variety, and these are all examples from Aotearoa New Zealand. So this is just to think a little bit more about the kind of journey of the volcanic gas from kind of volatile exsolution by the magma up to being emitted at the surface. And the modeling that we normally have been talking about and we'll show in exercise 2 is basically saying if I have a melt and I dissolve a bubble, what is the chemical composition of both those phases? So that's the volatile exsolution bit to start with. then what might happen is that gas is decoupled from the magma and it rises up by itself, so separated from the magma. And then there are a bunch of different processes that might affect it. So it could, if it's high temperature, it might react with the wall rock. And so it might precipitate different phases and it might change its composition. Even if it doesn't react with the rock around it, it might re-equilibrate kind of within the gas phase itself. So as you're rising to the surface, the pressure is decreasing and the temperature is decreasing. So you can get internal reactions going on. It means the speciation of the gas is going to be different from what was released from the magma. A lot of volcanoes host hydrothermal systems, so they're wet volcanoes, typically due to a lot of meteoric water. And when the volcanic gas enters this hydrothermal system, a whole bunch of other reactions will occur as well. So particularly in Aotearoa, Ruape and Whakaari are very wet systems typically, so we need to consider this as well. And we have a talk this afternoon discussing the hydrothermal system specifically for that. And then even once the volcanic gas enters the atmosphere and is released, it can mix with air. And if it's still hot enough, it might even react as it's mixing with the air. So there's a whole host of processes to consider. What we'll mainly concentrate today is ignoring most of these and just thinking about the volatile exsolution part. But it's important to think about that when you have a volcanic gas measurement. And there's lots of things that we can measure about volcanic gases. So we can look at their kind of chemistry, so the concentration of different volatile species and what speciation they're in, so if you've got water or hydrogen. And the reason we measure these is it can give you information about depth, as I showed in the first few slides. You can calculate the temperature of the gas before it cooled down sometimes, the redox state, so the kind of oxygen fugacity. It can be indicative of magma injection, but also hydrothermal reaction. We can also measure the isotopes. So there are a bunch of techniques for looking at, for instance, carbon isotopes, sulfur isotopes, nitrogen isotopes, etc. And we can even look at the isotopes of individual species. So we can measure like the CO2 isotopes, the carbon isotopes of CO2, but also the carbon isotopes of methane, for instance, if you have it. And the isotopes are great for really pinpointing like the source of where that gas has come from. So if you're looking at different tectonic settings, you might be able to see how much mantle influence there is in the arc setting or how much the kind of subducting slab is influencing it. And also if you've got input during its ascent to the crust. So for instance, hydrothermal interactions, you would see an effect of the water from meteoric water. The isotopes are also really good at telling if you've got open or closed system degassing. So closed system is where the melt and the vapor remain coupled all the way to the surface, whereas open system would be if that gas escapes. So obviously if you've got gas without an eruption, you have some sort of open system degassing. And then also equilibrium versus disequilibrium. So isotopes, especially like CO2, whether or not the melt or vapor becomes enriched in the heavy isotope of carbon is dependent on whether it's equilibrium or disequilibrium. And then we can also just measure how much gas is coming out, so the flux. And then we can sort of link that to maybe the amount of magma that's degassing, if there's new magma coming in. And then I've also written here hydrothermal sealing. So that's where essentially you've got precipitation of minerals in that hydrothermal system, and that can block the volcanic gas from being released. If it's released like catastrophically, that can lead to an eruption itself. But so even the absence of gas might tell you something about the volcanic system. For the rest of the talk, we'll just talk about concentration and speciation. So we'll have a look at what those species are. So this is a variety of volcanic gas compositions from around the world. And in these pie charts, first of all, I'm just showing how much of the gas is water and how much is everything else. And so essentially most of the volcanic gas is water. And that's just because water is a really major volatile species in melt. If we now kind of blow up that little everything else slice, so here I'm showing you the dry gas composition. So this is where I've just removed the water and renormalized everything to 100. We can see that we have a whole host of different species. So CO2 tends to be the next most common gas species. We then have the sulfur species, so SO2 and H2S. Then we might have the halogens, so HCl and HF. And then it's actually quite small here, but a lot of trace species. So things like hydrogen, carbon monoxide, ammonia, nitrogen, argon, oxygen, helium. But as you can see, those trace species are a very small part of the gas composition. And I should say this is all in mole percent. So typically gases are reported in mole percent. So I thought I'll just go through some of the ways of measuring the different these gas compositions, and I'll just talk through 3 different techniques in case people haven't got familiarity with them. So we'll talk about direct sampling, then a little bit about multi-gas, and then I'll just show that open path FTIR is also another technique. And I guess these go from in situ sampling to in situ, but you don't have to be there to measure it, and then a remote technique. So this is the first one is direct sampling. And I've just put this quote up from Kern et al. In 2022. To this day, analysis of direct gas samples still provides the most comprehensive compositional information on volcanic gas emissions. So the idea with this is that you're trying to take a quantitative sample of the volcanic gas. So you're trying to make sure you get all the species in the correct proportions in a little sample bottle. And this is an image of, geonet sampling at Tongariro volcano, and often these are done at fumaroles. So you can measure volcanic gases in those other emissions I showed you, but typically people try to do fumaroles because they're the kind of most pristine gas that you can collect. And so what you do is you put a titanium tube into your fumarole, you try and get a good flow rate, and you're trying to avoid as much as possible kind of atmospheric air entraining into that fumarole and kind of mixing. And then you're going to connect it up to your sample bottle. And this is what the sample bottle sort of looks like. These are called Giggenbach flasks, after Werner Giggenbach, who did a lot of his work in Aotearoa New Zealand. And essentially it's a glass bottle with a stopper at the top and 2 arms. And what we can do is we can evacuate these flasks so that there's no air in them, so that when we take them into the field, we can put our volcanic gas in. If we just took an empty flask into the field and we tried to fill it up with volcanic gas, it would be mostly water and then a little bit of CO2. And all of our trace species would be in such low concentrations. There'd be so few atoms of those species that it'd be really hard to measure. So what we do instead is we add this NaOH or KOH solution. And what this does is it actually reacts some of our species and means that they dissolve into this solution. So we can basically pass through more volcanic gas than our 300 milliliter bottle would have taken otherwise. So we can concentrate up those minor species, and I'll show that in the other picture. But this is just showing how we can evacuate it, and I'm not sure whether this is going to play. That sound is the sound of an evacuated flask. So it's like cavitation in there. So that's when we remove all of the air out of it. So there should be no bubbles in there. I just like the sound of that, to be honest. And this is showing what one of these flasks looks like while you're filling it up. So you've got this tube coming from your titanium tube. And to begin with, you just pass the volcanic gas through that until you're confident that you've got rid of all the air in your system. And so at that point, your flask is shut and your gas is passing through that T-junction. Then when you're comfortable that your system's all set up and you've not got any contamination, you put the clip on that you can see on the downstream end of your flask, and you tighten that up. And then you can open your flask up and start to bubble the volcanic gas through your KOH solution. You bubble it through to make all that CO2 react with it and go into that solution. The water is going to condense because it's colder. And then we also see these other species that go into the condensate. So things like H2S, SO2, the halogens and ammonia will dissolve into that condensate. And you end up trying to cool it down as well. So that's a bucket of ice. And that's to make the water condense, but also it speeds up the dissolution of CO2. And then what you end up with in the headspace are these non-condensed gases. So the helium, the hydrogen, oxygen, nitrogen, methane, etc. And essentially, because we can pass so much more gas through it, we're going to concentrate these up, and that makes them easier for us to analyze. I'm not sure how many people have measured volcanic gases, but it's quite a process actually to get that little one column of data. It will take minimum 2 days to analyze a sample because there's an overnight step, basically. You can do multiple samples in that 2 days, but it also requires a huge amount of lab equipment. So the first step is you're going to weigh your sample when it comes back, and that's just so you can work out how much water you collected. So you know the weight of the sample before you left, and then you know how much water has been added. The second step is to measure the pressure in that headspace, and that's going to allow us to calculate how many moles we have of the non-condensables. You then take it to a gas chromatography piece of kit, and you measure the concentration of those different headspace gases. So gas chromatography, basically you put your gas through a column, and that column, depending on the particular column, will separate out your gases in time. So you actually end up separating them all out, and then you can measure when they come through using various sensors. So gas chromatography, the only way you know what species it is by the time it appears, and you know what time you've calibrated for that. So if there are species that you're not expecting, you won't be able to fingerprint them using gas chromatography. You need to know what you're looking for. And in the analyses we used, well, when I was in New Zealand, we had 2 gas chromatography pieces of kit to be able to measure different species. Once you've dealt with the gas, you work out the volume of liquid, as that's going to go into our calculation. And then there's a bunch of wet chemistry. So go into the lab, and we do the CO2, the H2S, and the SO2 sort of by titration, essentially. And when I first got to GNS, it was by hand. And then we got an autotitrator. And this is one of the steps that takes overnight. The CO2, you have to oxidize the sample first, and you have to leave it overnight. But we can get these different species. Next, if you're interested in sulfur, you can actually precipitate out all the sulfur as barium sulfate, and then weigh it, and that will tell you the total sulfur that is in your sample. And then finally, if you want to know the halogens, you can measure them using ion chromatography. So similar to gas chromatography, you run it through a column, it separates out the different species in time, and then you can analyze them. So once you've done all of that, you then have to reconstruct the gas composition. And so we're going to basically add this all together and to get, in this case, I've shown some Vocari data, the total composition that there is for it. So yeah, when you see that one little column, a lot of work went into collecting that data. Now, obviously, direct sampling gives you the most pristine and I guess the most complete picture, but collecting a sample can take an hour or two. So it's obviously not going to be a continuous data set, and it's not going to be real time. So something that can be near real time and continuous would be the multi-gas. And so multi-gas is, I guess, a name for a family of systems which are still in situ. So you put them where the volcanic gas is being emitted, and they have a bunch of different sensors that allow them to detect the different gases in situ. So either you have a pump which draws in the volcanic gas and passes it through the sensors, or some of them they don't have a pump, they're just kind of exposed to the volcanic gases. And there's been a lot of work to work out what sensors we can use for different species. So water and CO2 are normally done by IR. Then there are a bunch of electrochemical sensors, which are in theory specific to different species, but I'll show in the next slide, they have plus sensitivities. And so we've got a bunch of different species we can now measure using electrochemical sensors. And then recently, Jessica's work here at McGill was looking at methane using a different sensor again, tunable diode laser spectrometer. And these systems have shrunk in size over time, and that gives us different applications we can use them for, which I'll show in a minute. But just to highlight with these electrochemical sensors, ideally we wouldn't be using them, but they're what we have to begin with, and people are looking at other techniques to use instead. But the issues are they have a response time. So when the gas concentration changes, it takes time for them to record that change. And so if you have different response times to all your different sensors, try to work out what the gas composition was at the same time. It'll be a little bit tricky. And you can see that response time with the curve at the start. They also have cross-sensitivity problems. So in an ideal world, they're only sensitive to one species. But you can see here when SO2 is injected, we see a response from the H2S sensor. So the SO2 is in blue and the H2S is in orange. So there's a little response there. And all of the sensors need calibration to check that they're reading the right numbers. And how often you need to calibrate depends on the kind of environment that you're in. And this is just an example of some multi-gas data. This is up at Ruapehu. And I guess the neat thing is it's really high temporal resolution. You can take a measurement every second. This is done every 10 minutes. It's near real time, so you can be telemetering that data. And it can be continuous, so you can be taking measurements all the time, compared to some techniques which rely on the sun, for instance. This does not rely on the sun, so you get data both day and night. And if you see these big drop spikes in this data, this is where we're calibrating. So we're running a zero calibration in real time as well to check that. And as I said, it's I've used the word multi-gas for a whole set of different sensors. And that's because this platform has been applied in lots of different ways. And so we've got John, a picture of John here. One option is a permanent station, so you can put it by your volcano and have it telemetering data in real time. So that's an example there. Some of these platforms have been put on aeroplanes to do gas plumes, essentially. So you can fly through the plume and work out the composition of the plume. A similar setup, it's not called a multi-gas, is in accumulation chambers. So if you've ever measured soil CO2 flux, where you basically put a bucket on the ground and let the gas accumulate, the sensors that you're using are essentially very similar to the multi-gas there. And then, as I said, they've been miniaturized and now can be put on different UAV platforms to be able to go into the plumes, much like the airplane option, but without people there. And then I just thought I'd at least show that another technique for measuring kind of full gas composition is open path FTIR spectroscopy. This is not one I've used myself, but essentially what it does is you have some source of infrared behind your gas. That passes through the gas, absorption occurs by the different species, and then you have an FTIR to record the spectrum of that. The source of IR can be like the sun. It can be an infrared lab that you take into the field yourself, or luckily, if there's an eruption going on, the lava is really hot, and that can be its own IR source. So people have done FTIR from like lava lakes, from fire fountaining, and from lava flows, and things like that. It can measure a whole variety of species. This is a list. There are some problems with, I guess, where species are absorbing in the same window. That has to be taken into account. But you can also get really high temporal resolution data, like multi-gas, but using this open path FTIR. And in comparison to both multi-gas and direct sampling, you can do this remotely. So you can be, I've seen some papers that were up to a couple of kilometers away from the event. So this is, I guess, a remote technique that allows you to get gas composition. And this is just a little bit about what the data sort of looks like. So what's collected is a spectrum. So you're getting intensity at different wavelengths. And what you're interested in is the absorption. And then you basically model that to calculate the concentration of all the gas species. And these are really tiny axes, I'm sorry. The second plot has got time on the x-axis and then concentration of a bunch of different species. And so you're getting that full gas composition like at high spatial resolution all at the same time. But these pieces of equipment, like they go into the field, but they're like, you know, it's not like the multi-gas. They're not small pieces of kit. And to run them is not like easy. So I don't think any are being run continuously remotely, as far as I'm aware. I don't think any of that have been like just like with the multi-gas, for instance. So I think just to summarize, I hope we have time. Sure. We can use volcanic gases often in volcano monitoring because they're really sensitive to like magma depth. The changes in the chemistry continue all the way from the volatile solution all the way up to like the plume. They're mostly water, and then with a bunch, I guess, of other species that are present. And there are a variety of techniques for looking at volcanic gas chemistry specifically, such as direct sampling as gas. Any questions? Do we have time for questions? Or do we...
Yep, we've got, well, it's eating into your exercise time.
Okay, well, or we can jump into yes. Yep. Anyone has got anything? Yes. So the question was about detection limits of FTIR and does it change? I don't know. I'm really sorry. This is not technical. So I have to. Has anybody got experience with FTIR in the room?
I think so.
Do you want to? Oh, can you turn your mic on?
I can try this. So it depends on the component you want to analyze. So for water and CO2, you're measuring the entire column from your instrument to the whatever your source. So maybe you're mostly analyzing what the humidity and CO2 in air. So that is really important. For other elements that are not present in air, like HCl, HF, SO2, this is much more, you can say, well, accurate or precise. Okay, so there are massive corrections for the air components like water and CO2. So the closer you get, the less you need to correct. Okay, so it varies a lot. Okay.
Okay, yeah, one more question.
Just to relate it, many of you are measuring melt inclusions and you use the Beer-Lambert law. And it's the same for these plumes. So the density of the plume, the distance that you are measuring through, and then what the previous man just said about sensitivity of different elements, that's the extinction coefficient for the different species, as well as the air contamination. So there you go.
Thanks. So maybe we'll go on to the exercises. So for these, if we can go back to our Victor, hopefully it's still up and running. And the idea for this is to, so the previous exercise, we were taking melt and fluid inclusion data and calculating pressures. Now we're going to try and run some degassing calculations. So taking a magma and then bringing it to the surface and seeing what its composition is in the melt, but also what the composition of the gas is. And the link to this, I guess, is ideally you would try and you'd measure your gas composition and try to link it to a magma depth for your from a degassing model.